Let's say you're making a cup of tea, so you boil the kettle. Where does the water go? Now, if you're like me, you're probably thinking it goes into the air, but have a think about that. The air is already full of air molecules, so where do the water molecules actually end up going? Well, they're going to need to take up some of the space. They're going to have to push the air molecules out of the way to some extent, and that means if they're pushing them, there's a force, so there's going to be some work done. What we're going to look at today is how much work is done as a gas expands. Let's draw it out. I've got a volume of gas surrounded by another infinite volume of gas. Okay, this is the one that's going to expand. Before that, though, let's consider forces. In fact, no, let's jump straight to pressures. The expanding gas has a pressure, PE, and let's just say the surrounding gas has a pressure, ATM, atmospheric pressure. It's the atmosphere. So how much work is done to expand the gas? Well, if we start with the defining equation, as always, which is W equals F times distance moved in the direction of the force. Okay, W equals FD, as long as we're thinking about displacement really. Force is PA, where P is ATM, the atmospheric pressure. It's the pressure of the gas it's expanding against. And we're going to assume that is constant. We're going to apply this force through distance D. So work done is PAD, which is PV, where V is the change in volume of the gas, not the absolute value of the volume, the change in volume. To clarify this, we'll write it as W equals P delta V, and that's a handy formula for work done by an expanding gas, assuming it is expanding against constant external pressure. And I'll leave you to think about how we can apply that simple formula to explain why it's cold at the top of a mountain.